Hello, my name is George Barrera, and this is the Impact Loading and Recovery of Copper team. We've got Ernesto, Guillermo, Javier, and Devin. Now the goal of this project is to design 5 projectile and target packages in order to study spallation of copper, and we'll be using a momentum trap and find the correlation between the predicted effects and experimental results in order to study the void nucleation and crack propagation.
Research into the field of high strain rate physics began with the work of Dr. John Hopkinson. His son Bertram was the first to document how shock waves could induce a fracture in a material without complete separation. Studies such as those of George T. Gray have observed the spallation of materials, and he also outlines the loading and recovery techniques. But no previous studies at the RFRL have focused on self-recovery of the specimen for further analysis. For our particular design, we want to cover a range of impact pressures from 1 to 3 gigapascals, and we want to aim for a pulse duration of around 2 microseconds. We have our momentum trap that we're using must be large enough to avoid edge effects in the target.
Okay, here's a little diagram of the 4 pieces that we're actually going to be designing for the AFRL. We have a projectile which encases the impactor, and there's one separate piece that's set downrange on the shock. Then next we have the momentum trap which encases the target. The momentum trap is set up at a 50-degree angle so that once it makes planar impact, it shoots the target right out to the soft recovery catch system. And all these pieces are held together. All these pieces are held together with an adhesive which connects the impact in the projectile, the momentum trap, and the target. Okay, here's another picture that shows you a little better thing what's actually going on in the experiment. We have the projectile right here. This is the projectile body. This all gets destroyed during the shot. The most important part here we're looking at is the impactor and the actual target and the momentum trap that encases it. And here's an actual picture of the projectile they used during the experiments. Here's a picture of how it's going to look coming down the barrel, making planar impact to the target, as we can see here. Okay, well it's not playing, but it makes planar impact to the target. The target gets hit, and it moves downrange to the soft recovery catch system for further analysis of the actual material.
So upon impact, shock waves will be created and will flow through the material. They will bounce off of the free surfaces of the copper target and the projectile and the impactor. When they bounce back, these waves are known as release waves, and they will continue to flow through the material and intersect. When they intersect, this creates a spall plane. This is what we're looking for. The spall plane, go ahead, will create voids and fractures within the copper target, and this is what we're going to analyze. These are some of the equations that we've used to calculate where the spall plane will be in the target. For the material selection, copper was used as the target because it's a very common material that the Air Force uses for many applications. Aluminum was also used for the momentum trap because it's very they have a lot of access to aluminum, and it gets destroyed every time the experiment is conducted. As you see in here, it's very light, but that is the target that we're going to be analyzing. And for the projectile, we use PMMA, which is also known as acrylic glass. And the reason why we use that is because it is more controlled, and we were able to use it for the lower impact pressures. We also used aluminum for one of the experiments to create the spall because the impact pressure was above the spall strength of copper.
So after we did our first calculations and we understood how wave propagation occurred on the target, we decided to do our first original design, which was the first impact pressure at 1 gigapascals. After all the calculations were done, we obtained a 1.03 gigapascal pressure with a 2.04 pulse duration, which is about the right numbers that we want here. If spallation were to occur and the void nucleation were to happen inside the target, we expect that 2.79 millimeter inside the target, the spallation plane, and we can observe that the effects from the momentum trap, the edge effects, will not reach the target in time, so cause any kind of clouding of the analysis. On your left, you can see the first engineering drawing for the projectile and the impactor, and on your right, the momentum trap encasing the target. Next one, please. After we did our first calculations, we decided to go the extra mile and do two design alternatives. The first design alternative was, we wanted to see a constant impactor plate thickness with 3.3 and 3.5 millimeters thickness. After we did all the calculations and the analysis of the predictions, we decided to go with a 3.3 millimeter impactor thickness, from ranging with speeds from 350 meters per second to 850 meters per second, assuming that the soft catch recovery system will be able to handle those speeds. The impact pressures range from 1 to 3 pascals as was the design specifications. They're not very accurate, but they are within the range that we want. For this next design alternative, which is B, we decided to go with variable thicknesses, which means that the impactor from the first shot will be different than the impactor from the last shot. Our thicknesses range from 3 millimeters to 3.85 millimeters. We wanted this so we can obtain a constant spall plane location. We could also obtain a constant pulse duration at the time. Since we're increasing the thicknesses and we're increasing the speed, the spall plane and the pulse duration will be kept pretty much the same. Next.
Okay, so our group met every Wednesday from 12 to 3 from the fall to spring semester. That was our meeting time, so we could actually separate topics and do our research and literature survey. As for work assignments, we covered different topics in the report and it was separated in that way. So someone did literature survey, someone did research, someone did global learning, so on and so forth. We also separated different tasks within the team, like team leader and team management. As we can here see, there's a cost analysis. We have 4 different cost analyses. We have labor, implementation, travel, and finally materials and manufacturing. We had a total estimate of 289 hours for every Wednesday meeting from fall to spring, and we put a price of $65 for the five senior design students. Then finally for implementation, we had 5 packages that were actually being tested. It cost $10,000 every shot at the AFRL, so it came out to around $50,000. And then finally for travel, to actually make it to the AFRL and check out the experiment and talk to Dr. House about how the experiment's set up and what he's actually looking for in our design analysis, it cost around $1,600. Finally, for the materials and actual manufacturing of the projectile impactor and the cost for the actual materials, it came out to around $2,000 for a grand total of $70,000.
As you can see here, these are the results of the first shot, and we did not expect spall to happen. As you can see, it did not happen. This is the recovered target on the top left, and under it is the momentum trap, and it breached about 30 inches into the soft catch system, which you see here on the right. And as you can see from the PDV diagram, which is the amplitude versus time, that what we want is from the left from 1.5 microseconds to 3.75 microseconds, which is the pulse duration. And that lasted 2.25 microseconds. Now afterwards, we aren't sure what this is. This is an anomaly. We have our various assumptions of what it might be. It might be that there's too much gap between the momentum trap and the target due to the glue keeping them together. Another possibility is the geometry of the momentum trap, the angle, and there's too much angle, or the actual physical properties of the copper.
For the second shot that was conducted, there was an error in recording the data, so we were not able to get the information to represent it in a graph. But those are the pieces recovered. We did not expect any kind of spall, but we didn't know for sure. So the this shot was done on a Friday, and the third shot was scheduled for the following Monday. So the fourth shot was designed as to redo the second experiment. Next slide, please. So this is the graph from the second experiment. Again, we do not see any kind of spall. We have our same anomaly occurring here, which our advisor still is doing research on it, on what it could be. But again, for the actual shockwave up in the front, we do not see any spall. For our third shot, we used aluminum because we wanted to do surface analysis of the copper from spall. As you can see here, the target plate was actually split in half, very, very clean, which we were not expecting. And as you can see here, the spallation continued into the momentum trap. This is the graph, and this is our spall. So we have, in the beginning, we have our Hugonio elastic limit, the Hugonio state, and then the pullback, and this is the wave of spallation in the material.
The assembly of the target and impactor components, it uses a very specific type of copper, and it requires laboratory conditions to ensure planar impact with the projectile. So it's handled by the IFRL. And this assembly is not really a design factor because the components are destroyed during the firing of the gun. Now, no maintenance is required for the target and the impactor because, as I just said, they're single use, and maintenance of the gun itself is going to be handled by the Air Force. The materials used in our design are readily available to the AFRL, and the production of these materials is not environmentally hazardous, so the environmental impact is not a great concern. And the only source of waste is from the machining and the finishing of the parts, which is a very small amount of metal every time that they're made. Our prediction methods, if validated by the experimental results, can be applied to other materials, and this is going to be useful anytime that a high pressure impact is involved, and it's going to increase the safety and reliability of equipment that has to deal with high pressure impacts. Now, the only problem is knowledge in this field is not very widespread, and there's a lot of research still to be done, such as we don't really understand too well how the stresses that occur just as spall begins, how it affects the physical properties of these metals, like how it affects the melting point, the yield strength, and its ability to be compressed. Next slide. Any safety risks that need to be accounted for during the experiment are handled by the safety regulations that the AFRL has put in place for their experimental facilities. And the major risk to our concerns is failure. Now, we define failure as having a spallation plane that is outside of the target area, so it's useless to us, we can't study it, having no spallation at all because then we have no results, or if we have complete target fragmentation, then we can't study the effects of the incipient spall.
So finally, we have completely recovered targets, which is a success for us. This is the first time so recovery is being performed by AFRL. We have achieved that. Then we have obtained one-dimensional separation and spallation in the target, which means that the momentum trap did its job and kept the edge effects from clouding the analysis. Now, we have also, next slide please, come down with two design alternatives, which means that we have gone the extra mile and given AFRL the flexibility to continue their work in this field after the senior design team stops collaborating with them. Next slide please. Also, our data validates our predictions, which means that we have been able to obtain the specific impact pressures that we desire with very too little error between the impact pressures. Where the error comes around is the pulse duration, since we're assuming theoretical conditions for these calculations. The pulse duration on the actual graphs have a lead and a lag, and that's why we don't obtain the exact numbers that we want. Next slide, please. So the future work for this, we have been communicated that the FRL has manufactured 15 packages, including PMMA as impactor and aluminum as well, with a copper target. So after they conclude all the experiments, they will do photomicrography and X-ray tomography on the samples in order to analyze and understand what's going on inside each of the samples. Here's a picture from a national laboratory where they conducted similar experiments, and this whole plane and Boeing nucleation will be something like that. Now, we want reproducibility of the experiments, and that's why they're going to continue doing these experiments throughout the year, trying to get the same results and the same anomalies to understand how everything is working. Now, after that, the final product will be produce behavioral traits of copper, seeing how it works and how it deforms and it behaves after shock loading, putting those specimens that have been shock loaded through quasi-static and dynamic loading tests. Next slide, please. Finally, they'll be moving onto different materials after a standard method has been set, with aluminum, magnesium, titanium, and beryllium, which are materials used in structures for the spacecraft. The application will be for armored vehicles and for space exploration in order to protect the occupants from space debris in order to maintain reliability of the spacecraft. Any questions?
Okay, very good.